Hello and good day and welcome to this webinar about microplastics organized by Sensilo. My name is Rudolf Jongma and together with my colleague Roesbe Aminian, we will host this webinar about microplastics. Today we have two guest speakers, Luten Agostinho and Eelco Pieke, who will tell you more about microplastics. At the end of the presentations we have 5 minutes for questions. During the presentation, you can ask your question in the chat box, and we make sure that your question will be asked to the speaker. Now I would like to give the word to my colleague, Roesbe Aminian.
Hello, everybody. My name is Roesbe Aminian, Research and Development Engineer at Sensilo. Here at Sensilo, we try to investigate different issues and challenges at water industry. But today we are going to focus on one of the important challenges at water industry, microplastics. Over the past few years, studies and research have indicated that the presence of plastic may have the adverse impact on the environment and human health. So let's take a closer look at it. Today we have scientists who've been working on this issue for a long time. But firstly, we are going to start with Dr. Luten Agostinho. Would you please introduce yourself, Luten, and share your presentation?
Yes, sure. Thank you, Roesbe, for the nice presentation, and thanks, Sensilo, for the invitation and the kind will to organize a nice webinar. Myself, my name is Luten Agostinho. I am a researcher here at WETS's European Center of Excellence for Sustainable Water Technology in the center of Leeuwarden, and I'm also a lecturer. I'm a researcher in one of our Habio Institute universities here in the same city, and I also stand in the University of Applied Science. I still have one more hat. I'm visiting professor for University of Twente, which is actually the position that brought me in contact with Roesbe in the end. Well, a very short outlook about the presentation. I will just briefly introduce you more or less the concept of the water campus here, so you know where we are. I will also give you, give you an idea about nano-microparticles in general, because we have here the objective of talking about the polymeric ones. But in our lab here, we have, we cover more particles, not only the polymerics, in this scale of micro and nano scale. Then I jump specifically for the polymeric ones. You see NMPs, because we normally use this acronym to nano microplastics. So we're gonna be, I'll be using this. I briefly mentioned about how we fabricate them, and that's one of the strongest points of our group, that we can fabricate these particles, and then I finished with some home messages. Well, the Water Campus Friesland, it is a complex here in the city of Leeuwarden, where we try to basically put many partners in the same location together, so we can easily cover the whole technology development line around water and wastewater treatment systems or water technology systems. So you can see in this diagram that we try to cover all the steps from the idea up to the moment that you get your product in the market. For that, of course, we need different partners. We cooperate with research institutes like WETSUS itself, Wageningen, Delft, UvA, and many other universities. These are, of course, just examples. We cooperate with technical Habio institutes, with applied science institutes, like NHL itself and Van Gaal, and other organizations like the Water Applications Center, CV and CIV. Of course, we have a very close contact in all these projects, in all this cooperation with companies, and we have also other institutes inside the Water Campus which are specifically dedicated to this company, let's say, this matchmaking cooperation market request, and this is the Water Alliance. We are in our group linked, as I mentioned, in this idea phase, meaning with the WETSUS Institute, and also here specifically linked to these institutes of the applied sciences. Specifically, I am the head of the Gilbert Armstrong Laboratory of Electrohydrodynamic Atomization, which is a initiative from Wetsus and NHL Standen that combine the use of, you can see in our logo, it combines the use of electricity, specifically high voltage, on the fabrication of nanoparticles and nano coating. So basically, when you try to bring this technique inside the water technology world, you can act in these five different fields: the production of nanoparticles, nanofibers, the production of coatings. For example, we work a lot with electrochemical industries and companies for production of electrocoatings, and we also work quite a lot with interfaces. And of course, because of our nature of Applied Institute, we are always interested in bringing these technologies to the market. Thus, we have also a strong focus on upscaling. Okay, now this is a little bit introduction about ourselves, and then now we go to more to the nano microparticles. Of course, you can find them in many different media, many different researchers. I'm also connected to some groups in Groningen and in Delft that are specifically looking for the presence of these particles in the air, for example, for air pollution. But yeah, what I'm trying to present here, given the fact of this, the nature of this webinar, but also the nature of the company that invited us, Sensilo, is basically focus on these particles in water, which is also, of course, our focus. So yeah, just a brief introduction. The nano microparticles you can see are particles, just to give you an idea of scale, by the European Union, they are considered particles which 50% or more of the population is in this range of 1 to 100 nanometers. So if 50% of your population is in this range, you can consider that you have a population of nanoparticles in your media. And you see that especially when you get down the micrometer size, you start to be very close to the molecular and atomic size. So for you to have an idea, the water molecule is in the range of 300 picometers, which would be 0.3 nanometers. And in our lab, we already are able to see particles in the range of 50 nanometers. So we become now very close to this range of sizes where you have actually molecules. And sometimes also, even you start to, if you go to some literature, you see that in water technology, we define suspended particles as particles that can be retained in a 0.1 micrometer filter. So officially, we measured particles of 50 nanometers in the lab, and we still consider, even though we still consider them particles which are suspended, according to some formal definitions, these particles can be already considered dissolved. Now that's a nice point, because then even if you go to this nanometric scale, you start to have some borderline of what is dissolved in your water and what is actually suspended in your water. Well, to give you an idea, most of these nanoparticles, they are present in form of metals, especially coming from the IT industry, titanium oxide, silica oxide. And if I give you an idea of production, you can find in many literatures that in Europe alone, we can produce up to 40 tons per year of these particles. They are, you can go to the literature, you find many different papers now about their presence, the metal-based. You see a lot of them is metal-based particles. Most authors have been focused on them, but you can also see from this plot published by Sousa also very recently last year, that the number of publications in this field has also considerably increased the last years. From in 2009, we did not have more than 5 publications per year. Now we have in the range of 30 publications per year, most of them in the toxicology aspect and remediation aspect, but you can also find removal, 18%, occurrence, 12%, and risk, 4%. Concentrations, mostly you can see again metal particles here, but in these metal particles analysis, the concentration are normally in nanograms per liter, and some very common ones like titanium and silver you can find also in micrograms per liter. Just to give you an idea, this is I put this, so can you find them actually in water? So this is just a tap water check that we have done last week in our lab here, and we were trying to just fine tune our machine. We used the FFF system, fluid fractioning system, to detect and to see these particles in water. And you just got tap water from the lab. We pass through the system. You can see. If you just look to this line, don't pay attention to the peaks. These peaks are just scattering peaks, but these are the sizes that we detect, which you can see is in the range of below 100 nanometers, and you can see also a quite big population of these nanoparticles, and that is just a tap water check, water from our lab. Well, if you want to check specific the polymeric particles, the polymeric particles, or we also know them as NMPs. They have one specific challenge, that they are very diverse. In which sense you can find, first of all, many different polymers: PP, nylon, PVC, PET, polystyrene, PON, whatever. They are, of course, most of them also. They contain some additives, which will make you think that the toxicology aspects of these particles are due to the particle itself, yes, but also due to possible compounds that can leach from them. Then that's what you can see here. Of course, you can also have different sizes. You have different morphologies. It could be a fiber, it could be a spherical, it could be a pellet, it could be a film. You have different colors, and of course you have different ecotoxins that can be linked from there. Another interesting thing is, of course, that this is a very recent publication, very interesting, from a group that we collaborated, a group from UvA and Wageningen, that they also have done some analysis, some review of how these microplastics, how these particles, they can be detected. And you can see, regarding the technique, the analytical technique, you can see for microplastics, you have different options, different authors that have used, for example, conventional filtration, cross-flow filtration, but you can use pyrolysis GC as a way to identify, or higher spectroscopy to identify them. But there is a special concern about the nano size, because mostly the micro size, I can say, that's also our experience in the lab, that the analytical support is mature or okay enough to start making good analysis, but for the nano side, not yet. When you try to see what is reported about their presence in water-based environments, you can see that they vary quite a lot. For this is work published in 2009 by Koemans. You can see that they range between this 10 to the power of 3 to 10 to the power of 8 concentration per cubic meter, and you can see as well that the variability of them is quite large, depending on which kind of sample you get, from wastewater treatment plant effluents to bottled water. Regarding current framework legislation, you can see that we don't have much done in that aspect, and that is basically because we also don't have much knowledge, especially once more for the nano size, for the nanoparticle size. We don't have much about the toxicology aspect. There's basically the plastic pollution is part of the legislation that addresses market authorization, the wider waste management policy, and addresses in environment legislations with especially emphasis on marine protection. The microplastics and especially nanoplastics are not explicitly mentioned within most of them, as you can see. But yeah, the risk-based legislation, as I said, has to be carefully done yet, and unfortunately we don't have, we are building a lot, so we already have quite a lot of information, but yet not enough in many different fields to come with practical proposals for this framework. So it's a work in construction, I would say. Yeah, fabrication. Well, but this is a general field. And now I just quickly talk about one of the things that we do here in the lab, which is the fabrication of these particles using electrohydrodynamic atomization. This is a very old technique. You can see here a picture of Abbé Nollet, which is dated from something 1832. That he was impressed when he was trying to do electrification tests with water, and then when he electrified the water container, he saw a spray coming out from it. So this is what we call it electrohydrodynamic atomization. So if you get a nozzle and you put a metallic piece close to it and apply a very strong potential difference between them in the order of kilovolts, the electric field will change your spherical meniscus into a conical meniscus, from where a jet emerges and breaks up into droplets, very small ones. You can see that from this picture, for example, that they are much smaller than the nozzle diameter itself, which makes this technology very interesting because, for example, with a 1 millimeter nozzle, I can make 1,000 times, 10,000 times smaller droplets. So I can do a 1 micrometer droplet. So if you imagine and you consider that we have our technology is now enough for the fabrication of nozzles with hundreds of micrometers, it means that I can use the same technique to produce nanometric particles. And we do this, so you can also play a little bit with your concentration. For example, if you have a high concentration of a specific polymer in a specific solvent volume, you can suppress, you can have the breakup in droplets, as I said, for low concentrations, but sometimes you can suppress this. And then instead of droplets, you can have ligaments. So you can make droplets and you can make fibers. So these are some examples of particles that we have been working in our lab. For example, this is PVP. You can see that we can go very low to the tens of nanometer size. And this is a work done recently by us as well, where we use nylon 6 to produce also nanometric fibers. Another thing that we can do if you actually use a double nozzle. So, for example, if you have, here I'm talking about the metal solution ionic liquid, but imagine that here outside you have a polymer and here you have a metal. What I can do is that I can produce these nanoparticles, but I can produce them with a metal inside. So these are some examples of hollow particles that we created with this technique. And what is the advantage? As you can see in these two papers, many scientists have been already trying to use this technique so they can make these particles traceable. As if you put a very special metal inside your particle like indium or palladium, then you can make your particles traceable in a way that, for example, if you want to test a specific water technology like sand filtration or any membrane type of removal technique, of cleaning technique, you can simply use a normal influent wastewater, river water, whatever, and you can spike these particles inside with this specific method and a metal, and you will be able to trace them in the outlet and therefore see if your technique is or not efficient to remove these nano microparticles. Well, some take-home message. This is the end of the presentation. Very basically, nanoparticles are overall present in nature. Most published works still focus on metal-based particles. We still lack some knowledge to support the development of good frameworks for NMPs. Electrohydrodynamic atomization can help producing some traceable particles, and Gilbert Armstrong Laboratory can provide the necessary support. So, hartelijk bedankt. Muito obrigado. Thank you very much, and I would like to very much hear to your questions if there are questions.
Well, thank you so much, Luton. Attendees, if you have questions, please write them on the chat toolbox. but we have some questions at the moment. Lytton, you were talking about nanoparticles. How do you retrieve these nanoparticles?
Well, in the very end, there are many different methods. For example, it depends on what you want to do. In the case of the production in the lab, we use HEPA filters, for example, connected to a suction device. So what you do is that you depends on the technique. So let's put an idea that we are producing polymeric particles in air using this kind of spray. So next to the spray, you can bring a suction system, which is connected to a HEPA filter, and then you can collect. So you have to just see what kind of filters you use, because again, the particles that we produce can be quite small, in the range of few tenths of nanometers. For hundreds of nanometers, these filters are okay.
Okay, thank you. I have another question. Do microplastics pose a risk in terms of chemical leaching in water?
Well, there are many different works in the literature that are touching upon this specific aspect. In our case here, we have done a review about the possible chemicals that can leach from plastic, and the answer to the question is yes, it can be. And it's hardly dependent on the kind of plastics you have. For example, for PVC, you can have some metals. For bottles, depending on the label, you can even have plumbum, for example. And we have also done some work to check the possibility of having phthalates and other chemical compounds.
Okay, thank you so much for your answer. We have apparently we have another question. If we want to use traceable particles to test the removal efficiency of water treatment technologies, can they be recovered for reuse?
No, unfortunately not. Unfortunately not. Once you use them, because what we do is we make them traceable and we identify them again by using ICP. And ICP is a plasma method, so you basically destroy them after they pass through your effluent. So this normally, especially if you use complex matrices like wastewater or river water, it's quite hard to retrieve them alone. Of course, you can remove them using some membrane techniques, but you don't just remove them, you remove everything in the same size or above that size. And
okay, thank you. We have another question. With all the research going on regarding nanoparticles, do you think we are estimating their presence in the environment?
Oh, this is a very difficult question. It is difficult for me to say, but when I just look at the challenges that we have still in the analytical part in the lab to identify these particles, I would say, yeah, there is a good chance that we underestimate their presence in the environment. Basically, because we also lack still some knowledge to identify them in this range. So in the range again of the hundreds of below the hundreds of nanometers, I would say yes. Most probably, even though I don't have enough data to refute this, to prove this.
Okay, thank you so much for your answer. So at the moment, I would like to start with our second speaker, Elko Pique. Would you please introduce yourself, Elko, and share your presentation?
Well, hello everyone. My name is Ilko Pieke and I am a advisor chemical water quality at het Waterlaboratorium, which is a laboratory that analyzes and researches mostly drinking water and water treatment plants of drinking water utilities, but also works on the general assessment of water quality, mostly in the Netherlands. So I am going to tell you a little bit about the macro, the micro, and the nanoplastics, a little bit less on the nano and a little bit more on the micro, in which the title is The Flip Side of All Proverbs. And I will get back to why we have a flip side there. It's always interesting to be the second or third speaker because you never know what your predecessors will do, but I think this will be a very interesting addition to the previous speaker. So I have a 5 count of topics that we're going to pass by. The proverb that I mentioned is out of sight, out of mind, and I will show you a little bit what I mean with that. I will also try to explain why would the water sector be involved in things such as microplastics. And then something more lab related, something more technology related is what kind of analytical strategies do you need to employ to monitor microplastics? And also a little bit of a preview of the results so far. So let's start with the title, the proverb. So the out of sight, out of mind, or in Dutch, uit het oog, uit het hart, is a very interesting proverb because it tends to be true a little bit more often than we would like. So in most cases, if I present these 2 pictures to people and I have to ask them, which one do you prefer? Which one would you prefer to drink? Most people would probably say the right one, even though it's probably not so smart either because they're seawater, it's not very healthy to drink. But the perception that something we see is more dangerous than something we don't see can be quite misleading. Because as we have learned in the past decade or so, is that when something disappears, it is a question whether it disappears or whether we just simply won't be able to detect it anymore. And that has been the case for macroplastics in the environment that are actually slowly but surely turning into smaller particles, into fragments, breakdown products, and eventually reaching the point where they are no longer visible to the human eye. And therefore the problem might seem solved, but we don't really know what these smaller particles are capable of, and we don't really know how much they affect the ecological system or the human health opposed to their larger relatives. So when things are disappearing, it is both a reason to be very happy because you don't see them anymore, but also a reason to be concerned because you don't know what is coming back because of them. So size matters for microplastics and plastics and nanoplastics, and that is not only because their visibility changes, but also some other properties are changing. So if a particle is decreasing, in a sense that it is fragmenting into multiple particles, we know that it will probably form more particles of smaller size, will probably lose mass in the process as well, because the fragmentation is never perfect. We will lose the ability to optically track the particles, and probably the most important one, we can probably expect them to have an increased biological potency. So that is actually tricky in the sense that if we look at what our visibility limit is, it is somewhere near the 40 micrometer mark if you have really good eyes and a good microscope. Anything below that becomes increasingly difficult to analyze, going towards the range size of a human cell. So in effect, larger particles are much easier accounted for than smaller particles, which in turn is also one of the reasons why the drinking sector is now getting involved. So if you look at the drinking water sector in the Netherlands, but also a little bit across the world, you'll see that quite a lot of water is produced from surface water, so from rivers or lakes or natural water bodies. Just to give you a little bit of an implication of how much water is actually consumed, if we look at the western region of the Netherlands, so the coast region, the amount of water extracted per year is quite significant. So we're talking about millions of cubic meters. So that means that you're talking about well, billions of liters basically. So a lot of water is passing through these water production plants, as we call them. So that is interesting because even if we would have a very low concentration of microplastics or nanoplastics, we would still, as a water sector, uptake a very large amount of particles per year. And that in turn makes the drinking water sector, especially in the Netherlands, a consumer of microplastics. So where we see that most consumers are actually emitters through things like plastic bags, but also through toothpaste, through cosmetics, the drinking water section actually gets more microplastics than it elutes. So as a consumer, it's interesting to know what is at our gate and why is it there. So the question then turns to measuring it, because obviously you can worry about it for a very long time, but you got to have some sort of evidence, some sort of information to put forth. So when you look at offline analytics, not just for microplastics, but for a lot of techniques, you basically have three pillars that are often used. So you have the sampling part, you have the cleanup part, and you have the analysis part. So for all of these pillars for microplastics, I would say they're all pretty much very much in development. So they're very new, they haven't been tested rigorously. So we have a lot of challenges there. So the goal of sampling in its very definition is to isolate microplastics or nanoplastics from their environment in sufficient quality and quantity and quality. So you want to really make sure they come out. So if we look at the current state of development, and this is mostly related to microplastics, we see that the common techniques used are filtration and fractionation. And I think for nanoplastics, it is not so different. So basically you use size differences to separate molecules from particles. You also see some very niche application of, for example, especially in water freeze drying or using liquid extractions. But by far the most common are to just filter your water. So just have a very narrow filter and make sure the particles don't pass through. So actually at our laboratory, so we also do microplastic analysis, which I should have mentioned before, but we do it. We use fractionation. So we fraction the sample into different size categories. Although it's not really that relevant why we do that, it is very interesting to see that the sampling itself has very many questions. So if we just look at a few of them that popped into my mind the moment I started writing reports and everything, is why do you sample? Like, what unit do you want to measure? Do you want to know how many particles are there? If so, what should their lower size range be? What should their upper size range be? Do you want to know the mass? Do you know how much microplastics you're expecting in the source? But there's also some more technical questions in the sense, how much volume do you want to sample? Do you want to sample 1 liter, 10 liter, 100 liter, 1,000, million? Or if you're talking about soil, how many kilograms of soil would you need? Then there's also the question, how long will you sample? So will you take a grab sample, so one big sample, or will you sample over a very long time? And how do you make sure you don't contaminate your sample with equipment or environment? So all of these questions are actually quite complex, and the current state of development is that we don't really have a good answer on these questions. We have some idea of what are the best practices, but in practice, sampling is probably the most important step, but also right now the most difficult one, because there's so many variables to deal with. So after sampling, the next step is to clean up your sample. The main goal is to remove interferences, so to make sure your analysis step goes as smoothly as possible. So the cleanup is a little bit, I would say, a bit boring, because the sampling step takes away a lot of cleanup already. So if you're filtering water, you're already taking away quite a lot of chemicals and background. So it's not obsolete, it's just a little bit less important in the microplastics in water discussion. Although I said that, you do have to do it most of the times, mostly because you want to remove non-plastic materials, for example, sand or particulate matter. But you also want to remove compounds that interfere with your analysis. So, for example, organic compounds that can disturb your spectroscopic measurement. So chemical digestion is often used to destroy everything that's not plastic. And then you often have some extra steps like reconcentration, refiltering. Density separation is used quite often to separate matter from microplastics. And you see some more niche applications as well, like enzymatic digestions, for example, for removing cellulose or for removing organic matter, and sometimes also some surfactant cleanup. Now, we use, and again, it's not that important for the rest of the story, just to let you know, we remove the non-plastic material using chemical digestion, and we also do some reconcentration steps. Density separation is depending very much on the sample. And the reason I'm telling you this is because there is not one clear method that is very suitable for all types of analysis. It's really a mix and match depending on how many microplastics are in your sample, how much interference is in your sample. So saying this is the best cleanup step, there isn't one. And that makes these analyses very complicated, and it makes the comparison of methods very complicated. So then assume you have cleaned up your step, and that's where the interesting part starts, is when you start analyzing. So, of course, the goal of the analysis techniques is often to determine the presence of microplastics or nanoplastics quantitatively, usually not so qualitative. So, in general, I would say that right now there are three main methods used based on different principles. Although there are, and this is mostly focusing on the microplastics, of course, you will find that actually most of these techniques don't really work that well for nanoplastics, except for the thermogravimetric. So we have the microscopic evaluation, which basically means using a very high zoomed lens to look at the particle, whether it's a microplastic or not. You have the spectroscopic analysis, which uses light at different wavelengths, and to see whether a particle is plastic based on what type of lights it absorbs. And you have the thermogravimetric, which is very simply just burning the sample and see how much of that burned part were plastics. So each of them have very different aspects. Our method is probably the simplest and most robust one, and also the one that sees the least is by microscopy. So just putting the microplastics under a microscope and analyzing them. It should be noted, and it should be emphasized, that all of these methods are heavily in development, in the sense that, like the sampling and like the cleanup, there is no clear-cut technique that severely outperforms all other techniques, and each of every one of these methods are usable depending on your research question. So you can have very distinct advantages and disadvantages. The size range depends a lot on the technique. For example, for microscopy, usually limited to about 50 micrometers, so relatively large plastics actually. For spectroscopy, usually limited 10 or 20, and for thermogravimetric, you can actually go all the way down to the nanoplastics. And there are some other things that matter as well, like how much are you bothered by background effects, like how much does the matrix matter? How much particles can you measure, or can you only measure the mass of the particles, or can you do both? And lastly, and not unimportantly, how expensive is it to run an analysis? Can you do it on a very large monitoring scale, or is it very prohibitive to use? So all of these aspects actually create the three pillars. It's very simple to show them. It's actually really difficult to fill them with a scientifically accurate and scientifically supported method. And that is one of the struggles, and it's probably the struggle you will hear about most in every paper regarding microplastics or nanoplastics. There is a very urgent and great need for standardization. So we need to standardize how we sample, how we clean up, and how we analyze, because only then can we start comparing data from different sources much more effectively. And as I said, there's multiple ways you will find this message communicated, and that's not some kind of lobby, just because it's painfully true. And it does actually hinder the development of knowledge on microplastics a lot. So moving away from the whole methodology behind the pillars, let's move a little bit in putting into practice, because that's where things get interesting and you start noticing the flaws of the theoretically optimal methods. So I'm going to focus on one project we did in the last 2 years for several drinking water companies, is to look at their drinking water production chains. So look at their purification efforts and see what happens with microplastics in the intake water when you start treating it, and how much of those microplastics remain in the outgoing water. And then another interesting question is, if you start distributing the water over very long distances, do you start adding microplastics again because you're using pumps and you're using pipes? So basically get an idea of how relevant are microplastics in a drinking water production. So in total, the project encompasses 36 sampling events, and it might not sound like a lot, but I'll get to a little bit why it isn't so easy to take a lot of samples. First reason already there is sampling volumes. If you have water that doesn't contain a very large amount of microplastics, or even do contain a lot of microplastics, if you want to take a homogeneous sample, you need to sample a lot. So for surface water, minimally, you would want to take 500 liters. So that's already quite a lot, and it's challenging in a logistic sense because you can't transport 500 liters of water to your lab. So you need to bring your lab to the water, take the sample, and go back. And you see the same thing for the more clean the water gets, the more water you will need to get a good number of microplastics for analysis. So if you look at drinking water, we like to analyze or sample at least 10,000 liters to get a decent estimation. So you can't transport those volumes, and you really need to move to the sampling location. And that's where it gets a bit tricky, because if you want to analyze if you have water in your tap water, so the water coming out of your tap, you ideally don't really want to do it with people at their homes, because they probably won't like the bill of tapping 2,000 or 10,000 liter of water. So you actually have to find places where you can sample securely while making sure you don't contaminate your sample with plastic, while making sure you don't have any rain or disturbances. So actually the practical part of sampling is much more complex than just deciding how much liter you're going to take. It has so many aspects to it. So actually, this is actually where we have sampled in the distribution area. So we actually, we know, of course, we are involved with the drinking water company. So we know exactly where there are places where we can sample. So we actually did it on the streets near people's houses. And it created all kinds of interesting situations where we just have a place in the middle of nowhere where we decide to take samples, because we know at that point there is like a certain distance, like 30 kilometers from the nearest distribution station, only to find how much water is in there. So sampling is not is quite challenging when you have to take such large volumes. You have to take a lot of precautions there. So perhaps what everyone has been waiting for so far is, what did we find? Well, of course we found microplastics, because that's what we're looking for. But we did find some things that are quite interesting to discuss, in that if we looked at the purification efforts, the first thing we notice is there's a very large variability in day to day. So the amount of microplastics you find on day 1 and day 2 can really, really differ significantly. And what we also saw was a general trend that during water treatment, so different treatment steps in the drinking water production, we saw the amount of microplastics steadily decrease. And eventually we also found that there were almost no microplastics or detectable plastics in the outgoing water. And we did the same thing for 3 different production chains, and we saw the same results for all of them. And then when looking at the distribution, so at the water that basically runs out of your tap, we saw basically a flat line, meaning that we didn't really find any differences between the outgoing water and the water you receive. So it seems that the distribution didn't have a lot of effect, or at least not in this range, because as I should notice, and as also written on the slides, we're only able to analyze microplastics larger than 50 micrometers. So we're talking about the relatively larger portion of microplastics, and not at all about the nanoplastics. So the question then, how much is in tap water? Well, these are numbers. What they basically mean that we sampled more than 10,000 liters of water coming from your tap, and we found a lot less than 0.1 microplastic per liter, and that is without correction of any possible blank effects from the lab or from the sieves themselves. So the most likely conclusion we had to draw out of this is that there are no larger microplastics in the tap water. Now, of course, that is the interesting conclusion, regardless of whether the data is accurate, regardless of whether you take into account. But there are some extra questions there, and probably the story behind the questions is a lot more interesting than the actual result. Is not only if you remove microplastics, where do they go? That's one of the questions. Like, you're removing them, but they have to go somewhere. They don't just disappear. And another one is that we didn't actually check or were able to analyze the smaller microplastics, so the 1 to 30 micrometers. And those are actually very relevant because they are probably biologically more active. The only problem is that the methodology behind those is poorly characterized. And on this part, I'm actually disagreeing with the previous speaker that said these methods are quite standardized. I think we still have a long way to go before we can actually compare these results properly. So the key message there is en route to standardization is exploration. So experience by doing, just by performing these analysis, performing these samplings, you learn a lot about the do's and don'ts of sampling. And you don't get those from a theoretically assessment. You just find out that actually applying monitoring is a lot more difficult than developing the method for it. This is just a nice picture to show you what kind of things we can actually encounter under the microscope. And it just goes to show, like, if you have to count the amount of plastics on the left, it's actually very complicated, regardless of whether you use an automated counter using infrared or whether you use your eye. It can be very difficult to start separating where does a fiber end and where does it stop. So counting microplastics is not as straightforward as it might seem. There's actually quite a lot of challenges ahead in there. I will just skip this slide for a bit because I'm looking at the time and it's getting a bit funky. But the complexity of data is one of the things to consider because the microplastic analysis delivers a lot of data with a lot of variables, and it's quite difficult to relate these to practical applications. So then I'm moving to pretty much the last real slide is what lessons have we learned from these early monitoring campaigns? Well, probably the strategic ones are that variable concentration levels. So for example, comparing wastewater influent to drinking water require very different strategies. There's no one size fits all strategy. So the sampling is different, the method is different, and that's also exemplified by the lack of standardization. So sampling and analysis are time consuming, which is not necessarily a problem, but the costs can be quite prohibitive. So it's not really a cheap analysis you would run 1,000 times per year just for the sake of it. You really have to think properly about where you want to apply it. And finally, communicating results is very, very difficult because there is no level of safe microplastics. There is no legislation on that part. So you're lacking context. So you can report it has 10 microplastics per liter, but what does that mean? And there is work going on this level, but it's still very early. And maybe on the technical side of things, for those of you interested in performing these type of analysis, grab samples we have seen repeatedly are very unsuitable. The natural fluctuation of microplastics can be very large. The sample preparation is very essential, also very difficult to do properly, and volume. So the volume matters. The more you sample, the more representative your sample is. So all of these challenges are actually, well, they're still there. So we're very early in development there. So I would just like to close off with some further reading. There have been some publications from the water sector on their research, on the research I'm presenting here now as well. So if you're interested in reading on that, they're available publicly. And perhaps also some other areas of interest in these topics is a recent research consortium that tried to stop microplastics from wastewater treatment effluent using a bubble curtain. The report has been published since this month, so it's a very interesting read. And also the Dutch Normalization Institute is working on a commission to start the standardization process of microplastics in the environment. So with all that due and said, I would like to close down my presentation. So thank you all for listening, and I guess if there's any questions, I'll be happy to answer them.
Okay, thank you so much, Elke, for your nice presentation. Actually, I have got some questions. The first one is, polymers are in general hydrophobic. How does this have an effect on filtering and analysis?
Yeah, that's a good question. I think the hydrophobicity of microplastics is not really that much of an issue. It does help them from stop being dissolved, at least in the state, but we haven't really looked into what happens in the purification. So do they actually absorb to, for example, because of their hydrophilic or hydrophobic interactions, or are they just size excluded? So it probably, for the smaller particles, it matters a lot more what kind of chemical interactions they have. I think for the larger particles, most of their actions will be based on their size, not necessarily on their surface.
Okay, thank you. And do you use reference materials for method validation?
Yeah, we have validated our method using several of these reference materials. We have some pretty good results, but we also know that microscopy is very prone to underestimating concentrations. So we are quite aware of that, and we've actually seen effects of that in the TKI study that I mentioned. That the closer you move to your lower size boundary, so for us that's 50 micrometers, but for example for IR that's 20, the more you start underestimating. So it's actually quite a risk that the closer you get to your lower detection limit, the more you start underestimating, because depending on the particle orientation, it can actually pass through a filter or not. So it becomes a bit tricky the closer you get to your lower level.
Okay. Aside from laboratory analysis of microplastics, do you foresee the development of online sensors for microplastic in the near future? Can online flow cytometers be used to this end?
So I would love to, because it would save a lot of work. I think it would, flow cytometry is something that has been playing on my mind a little bit. I know that Rijkswaterstaat, so the Dutch government institute, has experimented with it. They haven't continued with it, so I'm a little bit reluctant to say it works, but it would probably be the most interesting techniques, as it is pretty volume independent and can run online for a very long time. So I think online censoring of microplastics will be very difficult regardless of the technique, because you have to deal with low concentration, different size variations. You have a lot of background from sand, from other particles, from algae. So it becomes more and more difficult. So I think I would love to have it, but I think it's very difficult.
Okay, the last question is, in order to improve the analysis method for microplastics as a whole, what should be the primary focus of research and development?
That's probably the one question that you could ask. I think my approach would be first things first, which would be look at the sampling, the effects of sampling, because you can improve your analysis up to the perfect level, but if your sampling is off, it doesn't matter how good you analyze. And we have seen sampling effects that are very difficult to standardize. For example, the effect of rain, the effect of wind, but also the sampling depth. I mean, if you're really taking a surface water sample by a pump, for example, the depth of sampling determines the amount of microplastics and the types of microplastics you will find. So if I would say, where do we start? I would say sampling is definitely the place to start, and work your way through the method from that. And that's also one of the things I find lacking in the current development. You see a lot of focus on analysis techniques, and I do understand the need for them, but it doesn't matter how good your analysis is. If your sampling is awful, you will not get a good result. So ideally, they should all be developed, but sampling is crucial. It is extremely paramount in these type of problems.
And it gets even more complicated if you are not working with just drinking water. I imagine if you are collecting a sample from a wastewater treatment plant, I mean, you can get all possible different kinds of particles there. But by the way, we have good experiences we use in cross-flow water filtration systems, because you can be quite fast on concentrating like thousands of liters, and that in our experience that it could be a good way to accelerate and standardize the sampling system. Just to add a little bit. Sorry, Rosbeth, that I came in.
I think that's a very good addition, and one of the things we should mention is we are a commercial laboratory as well. So we're not just looking at which techniques are best, but which techniques are affordable, usable on large scale, usable in routine laboratories. So we have some more, I would say, some more complicated interests, because I've looked at the field flow fractionation, and those are extremely interesting. I just have a hard time imagining those at a commercial lab setup. So there's also and that's a deeper problem, is the need for data is much greater or much further advanced than the ability to provide it. So you have industry and academia mixing in these discussions. Both have very different needs. So it's very difficult to balance. But yeah, field for fractionation or 4F is very interesting technique for at least for concentrating your samples, and then you can decide to do something afterwards with it. But it is a very good technique to do volume reduction.
Okay, thank you so much for your nice conversation. Actually, here's the end of our webinar. Thanks to our speakers for sharing their thoughts and insight on this matter. Also, a thank you to our audience for participating at this webinar. If you have any questions or comments to what has just been presented, please feel free to submit these to support@sensilo.app. The recording of this podcast will be made available in Sensilo Toolbox via www.sensilo.app. Additionally, in the first week of June, we are going to organize another webinar on PFAS. More information will be announced soon by our media channels. Thank you so much, everybody. Have a nice day.